Oh, excellent. Thank you.
Okay, here we go. So, we're moving on to 1B.3 and 1B.4, where we introduce to you guys natural logarithms and Euler's number. So you can see EUL, so it's a German fellow pronounced Euler. And so Euler's number, I've got a description here of how that is generated. Now the physical reality of how it's generated isn't heaps important to us, okay? We don't really need to know where it comes from, just that we're going to be using it. And it's 2.72 approximately. It's like pi. We describe it as a transcendental number because it does have that sort of special meaning. That's really all we need to know, okay? But we're going to be using E to represent 2.72. Don't be alarmed by when you see it. It's just a number. Okay? It's just a number, just like 1 or 2 is a number. All right, I'll just get a razor here. Okay, so that's what E is. And so then when we're talking about a natural logarithm, that is a logarithm with E as the base. Okay? And we use Ln to represent a natural logarithm. Now, we've touched on logarithms in base 10 and other bases in year 11. For most of year 12, we're doing natural logarithms. Okay, for the majority of year 12. So let's get into it and have a look. And all of the rules are exactly the same. So if we have ln of e to the 2.2, because we have expressed this number as a single power of e, it just simplifies to be 2.2. Okay, in the next one we have ln of e to the x on 4. It's a single power of e, so it simplifies to x on 4. Now it goes without saying, you're going to see a lot of this kind of just sort of subtle shifting. X on 4 is the same as a quarter of x. Both of those are reasonable ways of representing it, and they mean the same thing. And you're required to sort of switch between both or recognize both. And we'll draw that out more as we get into calculus. Okay, here we have ln of e to the x on the square root of e. So it's not a single power of e, we need to manipulate it first. So we're going to use some index laws. The first thing we should do is express it as e to the x on e to the half. Alright? E to the x on e to the half. We've gotten rid of the square root. Now, because they have the same base, we can do the top power, take away the bottom power. Now we have expressed it as a single power of e. It simplifies to x take half. Okay. Now we've got e to the ln 4. We use e to get rid of ln. Okay, so what this is going to simplify to, we can look at the two rules that I've listed there. Ln e to the x is x, and e to the ln x is x. If we have e to the ln 4, it's 4. Right? We have e to the 2 ln 3. We can't answer that immediately. We need to get rid of this 2 somehow. Just like with other logarithms, the same rules apply. We can make that 2 a power. So we have e to the ln of 3 squared, which is ln of 9, right? E to the ln of 9. And we've expressed e to a single ln, so that simplifies to 9. Okay, before we can process this one, we need to add the powers together. They have the same base, so we could write this as e to the a plus b. Right, same base, so we can add those powers together. And now we've expressed it as a single power of e, so it simplifies to a plus b. Okay, one more absolutely fascinating connection here. Remember, if we have log of AB, we can write it as log A plus log B. All right, those same rules apply for ln. Have a look here. We have ln e to the a times e to the b. So we can split that. This is another way we could solve it. Ln e to the a plus ln e to the b. All right, we could split that using this log rule. All right, and then this is expressed as ln e to the a, so that simplifies to a. And this term simplifies to b. So there's two processes where you can generate the same solution. But it's really important we recognise all of those links. Okay, over here, we've got ln x equals 2. Now we're on to solving logarithmic equations. What you need to know when we're solving logarithmic equations is we want to isolate ln x and then get rid of it. How do we get rid of ln x? Well, we've seen e will get rid of ln, and ln will get rid of e. They sort of get rid of each other. It's a good way to think of it. So, we want to get x by itself. We're going to raise both sides, e to the power of both sides. Okay? In the first step of the equation, we have ln x equals 2. That the left side is equal to the right side. They're the same. And so if we raise e to the both sides, we've still maintained that equality. Excellent. And now e to the ln x simplifies to x. E squared remains as e squared. Remember, it's just a number. If e is 2.7, e squared is like 4.6 or something like that. Okay? So we've solved x and we've expressed it exactly. It's exact because it includes every possible decimal place. Okay. In B, we've got a little bit more unpacking to do. We want to, before we put e to the power of both sides, we need to isolate ln of x. So we're going to unpack it until we have ln of x by itself. The first thing we should do is subtract 3 from both sides to get rid of that. So we will have minus 4 ln x equals minus 2. All right, we've got negative on both sides, so we could drop it, but even then, we're just going to divide both sides by minus 4 to get ln x by itself. Minus 2 on minus 4. So we have ln x is half. All right. Now, how do we get rid of ln? We put e to the power of both sides. And it goes without saying that could be e to the 0.5. Now, different ways of presenting the same thing. All right, move on to C. We've got ln x squared equals 5. Now, there is a temptation here to square root both sides to get rid of the square, okay? That would be correct in one circumstance, but I need to point this out to you. ln of x squared is not equal to ln of x squared. Okay, they are not the same. So when we have ln of x squared, that's when the square just belongs to the x. It doesn't belong to the whole function. And so that means ln of x squared could be written as 2 ln of x. Okay? And in fact, that's how we are going to deal with it. Right? We're going to bring that 2 out front, so we have 2 ln x equals 5. We're going to divide both sides by 2, so we'll get ln x is 5 on 2. And then raise e to the power of both sides. Okay, again, e is just a number. All right, in D, we're going to want to collect the ln's. All right, so we have ln of 3x squared. Take ln of x. We can collect that. Remember, if we have ln a, take ln b, it's ln of a on top of b. So we can collect these together. That's going to be ln of 3x squared on top of x. Okay, the first one divided by the second one. And and that's equal to ln of 4. Okay, now we can raise e to the power of both sides. E and the ln will cancel each other, so we're going to have 3x equals 4, and so therefore x is 4 on top of 3. Okay, so there we were solving logarithmic equations. So let's look at the different parts we've done here. In question 1, we're introduced to the idea of simplifying natural logarithms and exponents. In question 2, we're solving logarithmic equations. In question 3, we're going to be solving exponential equations. Okay? We have done this sort of thing before. I'm just going to refresh it with you guys. First, we need to perform some factorization. So we need to recognize that 16 to the x is actually 4 to the x squared. Let's show you guys why. If we have 16 to the x, we can write that as 4 to the 2 to the x. And order of multiplication does not matter. So what that really is 4 to the 2x using the next order to expand. But 2 times 3 is the same as 3 times 2. All right? Which means we could express it like this: 4 to the x squared. Okay, so that's how they are equal to one another. So, and we can substitute that in. We will first. Let's do that first. We've got 4 to the x squared, take 5 times 4 to the x. And looking at that, it can be a little bit tricky to see how to factorize it. So here's that trick that we've been talking about for a while. Let's define a as 4 to the x. Okay, if a is 4 to the x, then what does our statement become? What does this equation become? If we substitute a in, we've got a squared, take 5a equals 0. And this is notoriously easy to factorize. Okay? This is a year 9 problem. We can see we've got a is common to both, so we can pull it out in front. And then we're left with a take 5 equals 0. There's the factorization process. Now let's apply the null factor law. A is 0, or a take 5 is 0. Okay, but we need to substitute a back in because we're not dealing with a, we're dealing with 4 to the x. So our solutions are 4 to the x is 0, or I might come up here for this one, but it's going to be a little bit more. Or 4 to the x is 5. Okay, so we have two solutions. Now, for any exponential, whenever you have any exponential to the power of x equals 0, there is never a solution. There is no solution. And the reason is, if you draw any exponential graph, it always has an asymptote at the x-axis. It never crosses the x-axis, so there's no solutions that make it true. Okay, that's always the case for exponentials equals 0. All right, if we have 4 to the x equals 5, we can now go ahead and solve this to find the solution. We want to get x by itself, so what we're going to do, this is what we did in year 11. This is a year 11 problem. We would log both sides. Remember, we can do anything we want as long as we do it to both sides. If we log both sides, we can now move the x out the front and divide both sides by log 4. Okay, another point of emphasis, a common, not really common, but every now and then you see pop up, people will express this as log of 5 on 4. That is not true. Okay, log of 5 divided by log of 4 is different from log of 5 on 4. Okay, so don't make that mistake. Okay, just turn the page, we're going to crank through these ones. So what we saw in the logarithmic equations is to get rid of ln, we have to raise e to the power of both sides, okay? Now, we've got e, so how are we going to get rid of e? We're going to put the natural logarithm of both sides. So I'm going to go here, ln e to the x equals ln 2. That's my first step. The first statement's equal, which means these are going to be equal as well. Okay, and ln e to the x equals x. Okay. Just like before, we need to unpack this a bit to get e to the x by itself first. That's our variable. We always want to isolate our variable. So first I'm going to take 5 from both sides. 1 take 5 is minus 3. We'll divide both sides by minus 3. And then we'll perform the natural logarithm of both sides. Okay, now with these answers I'm going to be continually pointing this out, like this could be represented as ln4 take ln3. Okay, that's another way it could be represented. Alright, so we're going to be seeing those a bit and making those connections. Are there any questions so far? Go. Splendid. Okay, we've got a couple to go. Here we've got c, we've got e to the 2x take 3 equals 11. Now we've already got e all by itself, okay? So that means we're ready to put the ln on both sides. That's going to be our first step here. And then ln of e to the 2x take 3 simplifies to that e and ln cancel, 2x take 3. And now this is just a linear equation for us to solve for x. Remember, ln of 11 is just a number. So first we'll move the 3 over the other side. Okay. ln of 11 plus 3 is not ln of 14. ln only belongs with the 11. Okay, so we can't collect those together. Then we'll divide both sides by 2. So a couple of ways to represent it. And both of those mean the same thing. Okay. In D, we have e to the x equals 9 on top of e to the x. I want you to think of that question like this. Like e to the x is a variable. Okay, well x is the variable, e to the x is obviously the variable term. We can think of it like this. It's x equals 9 on top of x. How do you solve a problem like that? We need to get all of the variables on one side. So your first step here would be to multiply both sides by x. Okay? Because then what that's going to do is cancel here. So you'll have the variables on one side and the number on the other. So we need to do the same for this one. Let's multiply both sides by e to the x. Remember, you can do anything as long as you do it to both sides. So this is for D. Times both sides by e to the x. It's going to cancel at the bottom. Here we can collect these. If we have e to the x times e to the x, they have the same base. So let's add those powers together. This is e to the 2x equals 9. All right, now we're ready to ln both sides. (2x) equals ln of 9. X equals half ln of 9. Now, I'm going to accept that as a final answer, okay? But if you were to look in the textbook for a question like this, they would write ln3. Why? Who can see?
You do like ln 9 to the power of half, which
Very
is
good.
square root of 9.
Very good, yep. If we take that half up there, that's the square root of 9, which is 3. Okay, so different ways of representing things. I'm going to accept basically anything as long as you've isolated x. Alright? But the textbooks are very fussy. Okay, so don't be alarmed when your answer doesn't match up with theirs. That's where you can use the work solutions to see how they got to a certain point. Okay, very last one. We have 2 times 0.6x equals 10. This is an exponential equation. We've solved these before. Over here, we did it with a logarithm in base 10. It doesn't matter what we use, okay, but for year 12, generally speaking, we're going to use natural logarithms. So first we want to isolate the exponential term. That means we want to get rid of 2. Okay? And now, okay, one more thing that goes without saying. 2 times 0.6 to the power of x is not 1.2 to the power of x. Okay? That's bad maths. That would violate bed maths, okay? First you have to do exponents. Alright? So we can't perform that. We're going to divide both sides by 2. We'll have 0.6 to the x equals 5. Okay? Then we're going to put the natural logarithm on both sides. ln of 0.6 to the x equals ln of 5. We'll move the x out the front. And there's our final answer. Okay, so let's see how you go tonight. Probably spend, I think, about an hour working your way through 1B. You're probably on 2 now, 2, 3, 4. Just try your hardest to finish it off. Don't be alarmed if you come back and you haven't done it all by tomorrow. Okay? Good work.